Thank you very much, Vitaly, particularly for this opportunity. And also I want to apologize in advance for shameless advertising another book. The reason I'm doing it is because this book actually came out just when the pandemic hit. So I never got a chance to to extol its virtues. But for those of you thinking about teaching intermediate microeconomics, I'd urge you to consider this if you're looking for something different. Now, what I'll be talking about today is joint work with Thanh and Nguyen at Purdue. You should feel free to ask questions at any time. I prefer oral questions, but I've also fallen into the habit of just looking at the chat box rather than your faces. So you should feel free to ask questions through the chat as well. What is this paper about? It's about competitive equilibria with indivisible goods. And so let me quickly summarize the two sort of main results that we have so that they don't get lost in the details. As all of you will know, when you have indivisible goods, competitive equilibria are no longer guaranteed to exist. And what we do in this paper is we identify prices at which the excess demand for each good is going to be bounded by a parameter, and that parameter is going to depend upon the preferences of the agents, and importantly, it's going to be independent of the size of the economy. Now, this kind of market clearing price arrow called a social approximate equilibria, meaning a collection of prices and demands where the excess demand for each good is in some sense small. Okay? Whether this result is useful or not is going to depend on the bound that you have on the excess demand. And I will offer at least one application where I think that bound is going to be small enough that it's useful for applications. The second result that we have is a byproduct of this first result, which is an extension to the usual sufficient conditions on preferences that guarantee the existence of a competitive equilibrium. So some of you will know that these sufficient conditions typically hold for quasi-linear preferences. We will give you a sufficient condition for existence of competitive equilibria with non-quasi-linear preferences. So those are the two technical results of this paper. Why on earth should you care? And the reason you should care is because when we design pseudo markets, artificial markets, competitive equilibrium outcomes are sometimes used as a benchmark. Why? Because when a competitive equilibrium outcome exists, it's in the core, it's Pareto optimal, and under certain conditions satisfies fairness properties like equal treatment of equals and envy-freeness. So this is why I think one should care about the existence of competitive equilibria. Okay. Now, I mentioned pseudo markets, so let me say a little bit more about that. Frequently, within organizations and firms, one has to allocate scarce resources, and there is no internal market within the organization to do that. Two obvious applications of this setting would be assigning faculty offices to faculty, and the other is assigning courses to students. Another example that we typically don't think about, but that would also be relevant, would be how Disney, for example, manages the crowds and congestion at each of its rides. In all of these cases, agents pay some kind of entry fee, but there are no well-defined property rights, right? So, and there is no money that allows the agents, for example, in the Disney case, ostensibly, to trade off. In other words, I cannot sell my place in the queue for one ride with your place in the queue for another ride. I do not have a way directly to pay you to jump in front of you in the queue. Similarly, with faculty offices, we typically don't rely on money to decide which faculty member gets which offices, although there have been departments at some time that have introduced money by asking faculty to pay with their research budgets, but that typically generates protests and arguments. And certainly when we assign courses to students, we often do not ask students to pay a premium for particularly popular courses. So in each of these cases, in order to make good or desirable allocations, we might introduce artificial currency and then have the agents trade in some way. Okay? And this is the reason for the interest in pseudo markets. Let me pause here in case there are questions. Okay. Now, how has prior work dealt with the non-existence of competitive equilibrium with indivisible goods? Well, one is by restricting the preferences, and typically this restriction rules out all sorts of interesting complementarities. And perhaps the most well-known paper in this line is the classic paper of Kelso and Crawford that introduces this restriction called gross substitutes with quasi-linear preferences, and shows that when all agents have such preferences, a competitive equilibrium in an economy with indivisible goods exists. Okay? If you think about some of the applications I mentioned, in particular the course allocation one, agents are interested in consuming bundles of goods, which is a collection of courses, and there could be complementarities between these courses. And so therefore, these preference restrictions are not particularly helpful in those settings. The second approach to dealing with indivisibilities is to basically drown them by making the market very large. And if you think about the motivating application as being designing pseudo markets within organizations, it's hard to imagine that the organizations that one has in mind are going to be of the scale at which these papers, for example, Azevedo, Vale, and White, I apologize for leaving his name off, would be relevant. The third approach is an old one, which is we eliminate the indivisibilities via lotteries. We can always make something indivisible by handing it out using probabilities. But this raises a technical difficulty in the sense that we are now asking about lotteries over allocations of goods. And so the space of allocations is potentially very large if we are allocating goods to agents who are interested in consuming bundles of goods. So that poses something of a technical difficulty in identifying what is the feasible space of lotteries that you get to choose from. Okay? The next approach is popular amongst computer scientists, which is let's propose a notion of approximate competitive equilibrium. And typically these notions are based on a cardinal measure of welfare. And the goal is to get an approximation, in other words, some allocation, prices and allocations that generate a welfare that scales slowly with the size of the economy. In other words, the gap between the welfare that you achieve and the best possible welfare, that gap should scale slowly with the size of the economy. Okay. In my view, this is overly restrictive because you have to rely on this cardinal notion of welfare that I think could be problematic in some applications. Last approach is the approach that we follow, which I said comes from Arrow, which is to look at social approximate equilibria, find prices where you get approximate market clearing. And there were 3 early papers in the 70s which attempted to do that. But if you look at these papers, the bounds on the mismatch between supply and demand that they give depend on parameters that have to do with the size of the economy. In other words, the number of agents or the number of goods. And so the approximation results are typically of the form, well, keep one thing small, let the other thing get big, and then we have a reasonable approximation. Okay? And to our mind, this is unsatisfying. Okay? So as I said earlier, we are going to look at social approximate equilibria, but the bound that we're going to give on the mismatch between supply and demand is not going to depend on the number of goods or the number of agents, but instead on a parameter that summarizes the preferences. Okay. So now let me introduce notation so that I can state this result that I've alluded to precisely, and then say a little something about how it is proved, and then finally discuss an application to course allocation. So I'm going to use capital N, M, to denote a set of indivisible goods. A bundle of goods is denoted by a vector X with integer, non-negative integer components. And this vector X should live in some bounded set, meaning that no agent is going to be interested in consuming an infinite number of any good. In particular, for this talk, I'm going to begin by restricting attention to the case where each agent is interested in consuming at most one copy of each good. So I'm interested in consuming many goods, but only one copy of each good. Okay. And if you think about course allocation, that is perfectly reasonable. I don't need 2 seats in a particular course. I only need 1. But I may be interested in a variety of courses. Okay. The utility for a bundle X and a transfer T, I'm going to denote by U of X comma T. And the assumption I'm going to impose on utility is that it should be continuous and non-increasing in the transfer. Okay. And just to remind you, quasilinearity is a special case where your utility can be decomposed into 2 parts, a value for the bundle minus the transfer. There'll be a price vector, which is going to live in m-dimensional space, which is the cardinality of the number of goods. And what is your choice correspondence at a price P? It is the set of bundles at price P that maximize your utility. And 2 more pieces of notation. The first is x minus y superscript plus. This is simply the vector whose ith component is the larger of the difference in 0. So I want to keep the positive part of x minus y. And the second is simply a way of writing down the L1 norm, because the L1 norm is going to play a role in what I'm about to describe. So the L1 distance between 2 vectors x and y can be written as basically, the positive part of x minus y plus the positive part of y minus x. Now, why am I emphasizing what is ostensibly a triviality? It's because this allows me to interpret the L1 distance between x and y in the following way. If you think about x and y as 0, 1 vectors, so they refer to a bundle of goods where you're consuming at most 1 copy of each good, then the L1 distance between x and y is simply a measure of the number of goods that I have to swap out of x, and plus the number of goods that I have to take from y and put into x so that x will become y. So in other words, it's the number of exchanges that I have to perform to move from the bundle X to the bundle Y. Okay. Any questions so far? Okay, so here is the important condition. I make no apologies for the fact that this seems like a rather abstract condition. Later on, I will try to persuade you that it has a reasonable interpretation. So once again, for the purposes of exposition, I'm going to assume that agents consume at most 1 unit of each good. And here is the definition. The utility function satisfies what we call the delta substitutes property if for any price vector, the L1 norm of each edge of the convex hull of the choice correspondence is at most delta. Okay. So let me draw a little picture. I announce a price vector P. At that price vector P, you tell me which bundles you wish to consume. Here they are. So these are the bundles that maximize your utility at price vector P. I've written down 4 dots. That's your choice correspondence. I now take the convex hull. That's the convex hull of your choice correspondence. And the condition that I am imposing is that if I look at any edge of the choice correspondence, so this is bundle X and this is bundle Y, then the L1 norm of that edge is at most delta. Okay. Now, notice this is why I'm assuming that that you're consuming at most 1 unit of each good. That means my vectors X and Y are binary vectors. There can be no vector inside this that corresponds to a binary vector. Okay. Now, this is important because, and is sometimes overlooked in other papers, which typically go directly to allowing agents to consume multiple copies of a good, which is that you could end up with bundles that are inside the convex hull of your choice correspondence that may not be utility maximizing. By restricting ourselves to binary vectors, we avoid having to deal with those bundles. Now, we have a way of dealing with them, and I'll mention that later on. But it means that we do not have to make a commitment about what are the utility properties of these bundles. Other people make that commitment by imposing an additional condition on the utility function, specifically concavity. Okay. Okay. So does everyone understand this delta substitutes condition? Okay, as I said, it seems like a very abstract condition. Now let me convince you that there is an interpretation for it, and here it is. It is equivalent to something that you might find more natural, which we call delta improvement. And those of you who are familiar, for example, with the papers by Gould and Stacchetti and Kelso-Crawford, you should be thinking about single improvement, which is a special case of this. So take 2 bundles in your choice correspondence, X and Y, and now imagine I change the price vector in such a way that the price of X goes up by more than the price of Y. So initially, you're indifferent between X and Y. I now make a change in the price vector. If I make that change, then this improvement property requires the following. You can find an integer vector A that lives in the positive part of X minus Y, meaning you can find a subset of objects that lives in X, but not Y. You can find a subset of objects that lives in Y, but not X. Okay. Okay. The number of such objects should not be large, meaning at most delta. with the following property. If I swap out the objects in A and I put in the objects in B, I still live in the choice correspondence. In other words, X has now become slightly more expensive than Y. There should be a way to swap things out of X, put things in from Y, and still be in the choice correspondence. And then the last condition I need is that this new bundle, its price should have increased also by less than the price of that X increases. Now we have a theorem in the paper that says this condition is equivalent to delta substitutes. So roughly, so what I'd like you to interpret this to mean is delta substitutes basically means I can go from one bundle to another in my choice correspondence that are nearby by swapping at most delta items. If I specialize to quasilinearity, I get an even simpler condition, which simply says, supposing you give me two bundles X and Y, where bundle Y utility dominates bundle X, then I can move from X in the direction of Y by swapping at most delta items and improve my utility. Yes, Naomi, there is a relation between delta substitutes and gross substitutes, and this is what I'm about to describe next. So I'm first going to describe the single improvement condition of Gould and Sticchetti. So in their paper, they had quasi-linear preferences, and agents were interested in consuming at most one copy of each good. And what was the single improvement condition? If bundle Y generated strictly more utility than bundle X, then there was a good in X, but not in Y, and a good in Y, but not in X, that you could swap into X and improve the utility that you get. So what they meant by single improvement is I could get from a utility inferior bundle to a better bundle by either deleting an object, adding at most one object, or swapping at most a pair. Okay. How does delta improvement differ from this? We're simply saying replace the one by a delta. Why restrict yourself to either 1-for-1 exchanges? Why not allow 2 for 3, 3 for 4? Right? But the total amount that is exchanged should be at most delta, is essentially what we're asking for. Okay? So we're relaxing the single improvement condition. And now the answer to your question, Naomi, was in the paper by Gould and Sticchetti, they showed that single improvement was equivalent to gross substitutes. So yes, there is a relationship between delta substitutes and gross substitutes. Gross substitutes is a special case of delta substitutes when delta is equal to 2. Did I answer your question, Naomi? Now, gross substitutes imposes actually an additional condition beyond this cardinality condition. So in other words, it's not simply a matter of delta is 2, that gives you existence of competitive equilibria. There's an additional condition in gross substitutes, which I will mention in a moment. Let me remind you of what gross substitutes is. Agents consume, again, at most 1 unit of each good. And basically, gross substitute says, look at the bundle that you consume at price vector P. So the bundle that, look at a bundle that maximizes your utility at price vector P. Now raise the price of one of the goods. then at the new price vector, there must exist a utility maximizing bundle with the following property. It contains every good that lived in X whose price did not change. So gross substitutes basically means that if I raise the price of something, the only thing I can do is either not change my consumption or drop that good, and put some other good that I previously wasn't consuming in my bundle. Okay. Here is a generalization of gross substitutes to the non-quasi-linear case, which we call geometric substitutes. And this is related to the extra condition that gross substitutes is imposing. Again, I look at the convex hull of your choice correspondence. Here it is. In addition to the L1 norm being less than or equal to 2, I need another condition on the sign pattern of the vector x, which is it consists of either zeros and zero, ones, and -1, and at most 2 non-zero entries, and those have to be of opposite sign. So this is the extra condition that you need with gross substitutes, and under that condition, here we're not requiring quasilinearity, right? This holds for any u of x, comma p dot x, subject to the continuity requirement on transfers. And under geometric substitutes, we can show that a competitive equilibrium exists. Okay. Okay. And in the non-quasi-linear setting, this is not the same as what you might think of as the natural generalization of gross substitutes to the quasi-linear setting, non-quasi-linear setting. This is a different class of preferences. And again, this class of preferences has an interpretation in terms of an improvement property, and we've written down a version of what that improvement property would be. And again, we have a proof of the equivalence of this to geometric substitutes. Okay. And finally, let me just mention that all of the results I'm about to describe and all of the definitions I gave will extend to the case when agents consume multiple copies of a particular good. And the reason we can do that is if they're consuming multiple copies of a good, let's say an orange, and so let's say they consume 3 oranges, then the trick is fairly straightforward. Every copy of an orange gets its own name. So orange number 1, orange number 2, orange number 3. And then with this trick, all of our definitions and theorems carry over to the case of non-binary bundles. And now let me tell you about the kinds of theorems that we can prove. Okay. So first, I'm going to remind you of the definition of a competitive equilibrium. Okay. So I have a set capital N of agents. Every agent is endowed with a utility function. There is a supply of good I. Si is the supply of good I. Little s is the supply vector. A competitive equilibrium is a price vector P. And demands, which live in your choice correspondence, which are integer vectors, such that total demand is less than or equal to total supply, with equality for any good with a non-zero price. Notice I am not requiring the usual condition, which is this. And the reason I am not requiring this condition is because there is no non-satiation assumption that we are invoking in the preferences, which means we have to allow for the possibility that some goods get thrown away. Okay. Another thing to keep in mind is that when you drop the non-satiation assumption, not every competitive equilibrium is guaranteed to be Pareto optimal. So there is also a selection issue that you have to worry about. but we have theorems from Mascarell and Andrew McLennan that tell us about how to select such equilibria when the non-satiation assumption is thrown away. Okay, this is the definition of a competitive equilibrium. Okay. And now let me forget this is an example to show the geometrics. Here is, I think, the important result. So let me describe that. This is the social approximate competitive equilibrium. If all agents' preferences satisfy the delta substitutes property, then for every supply vector S, there exists a perturbation of the supply vector, which we're going to call S prime. So that perturbation differs from the original supply vector. Good by at most delta minus 1. And we can find that, and we can guarantee a competitive equilibrium with respect to the S primes. So in other words, I cannot find necessarily a competitive equilibrium for the economy that you give me, but I can find a competitive equilibrium for a nearby economy. Nearby in what sense? I am going to perturb the supply vectors. So that's the sense of nearby. Why do I use the word nearby? Because the perturbation involves altering the supply of each good by at most delta minus 1. Notice delta does not depend upon the number of agents or the number of goods. This is simply a restriction on the preferences of the agents. In other words, if the agents can get from one bundle to a utility improving bundle by exchanging up to delta goods, okay, then this is the bound. Okay. Now, why might this be useful? Actually, let me say a little bit about how we prove the result. The first step is to construct what's called a pseudo equilibrium. What is a pseudo equilibrium? I take your choice correspondences and I convexify them. In other words, I operate. Oh, go ahead, Peter, you had a question.
One question is of interpretation. So one way to interpret this is, let's say, an exchange where there's a specialist or a market maker that can engage in trade on behalf of the exchange. And one way to interpret this is that it's the exchange performing some quantity of trades to take us from S to S prime so that we have a competitive equilibrium. Is that a reasonable interpretation?
Okay, so I think that is a correct interpretation, but in the exchange context, I think I would find it difficult to accept this as a useful interpretation. So let me give you an alternative interpretation, which I think so when I say it, no. What I'm going to give you is another environment in which I think the interpretation that you've advanced makes more sense. Okay? So the application I have in mind, for example, of such a result is the following. I am allocating courses to students. Every course has an upper limit on the number of students who can take it, which is determined by the fire marshal's limit on the number of people that can be in the classroom. So this is certainly true in the US. You go to a classroom, there will be a sign and it will say no more than 50 people in the classroom. Okay. It is also the case in a US university. Most students are typically taking only 4 or 5 classes a semester. And so therefore, no student is interested in a bundle that exceeds size 5. Now that means the maximum number of swaps that a student has to engage in to get from one bundle to a utility improving bundle will involve no more than 5 objects. right? So delta is at most 5. Okay. So if I plug that in, I get 5 minus 1, which is 4. Now that means I can find a competitive equilibrium allocation where some classes will have a number of students that is up to 4 less than the capacity, and some might end up with 4 more than the capacity. Okay? Now, let's think about the overcapacitated classrooms. Do I have to worry about them? As a practical matter, no, because the only time all students turn up is in the first class and the last class. Absences and other things will take care of the 4. But, the university is interested in being compliant with the fire marshal's limit. So what this would mean is I go into every classroom and I remove 4 seats. Then I compute the competitive equilibrium, and I know that I have in reserve for every classroom up to 4 seats, so I can fulfill all of the demand. Now, notice I am burning some supply because I'm removing 4 seats, and I may end up only returning 2 back into the classroom. So I interpret the delta minus 1 in that context as the cost that the university pays for making an indivisible good divisible. So does that interpretation make more sense than the one that you offered, Peter?
Well, let's see. I'm just still, I really like actually the use of the market maker as making some small amounts of trade in order to establish uniqueness and existence of competitive equilibrium in situations where there's complementarities that aren't that big. So anyway, we should have a discussion offline about the issue, and because I think it actually is a lot of practical applications, but we can take that offline.
Well, okay. So maybe I should, rather than offer an alternative, I should explain my hesitancy, and you can cure me of it, which is the concern I had with the market maker story is that the market maker might have to subsidize some trades and was therefore losing money. And that's, I thought that's something that I thought somebody might hesitate at suggesting, right?
Yeah. So in my experience is that the market maker actually is making money, and the reason is they're basically stepping in and providing arbitrage where, for some reason, the market itself isn't providing that arbitrage.
I see. Okay. So given the time constraints that Vitaly had stipulated in his invitation, I'm going to skip the discussion of how we get these results. I'm happy to talk about them offline. Maybe it will be a good idea for me now to go directly to the application, since I've mentioned course allocation. And there is a natural paper that that should come to mind, which is the paper by Eric Budish in the Journal of Political Economy on course allocation. Okay. Now, Eric also proposes a competitive equilibrium allocation scheme for assigning courses to students. Eric's paper is inspired by the classic paper of Hilland and Zeckhauser, which gives to every agent the same amount of fictitious money, equal incomes. But there the agents are interested in consuming at most one good. So Eric's paper extends that to a setting where agents are interested in consuming bundles of goods. And for that setting, he also develops a social approximate equilibrium. And in this language, his social approximate equilibrium can be thought of as providing the following guarantee. He will give you a competitive equilibrium allocation in a nearby economy by perturbing the supplies. But the notion of nearby is in terms of the L2 norm. And the bound that he gets is this, where M is the number of courses or the number of goods. Okay? We, notice, are offering a bound that holds good by good. T is offering a bound on the Euclidean distance between the supply and the demand vector. The two bounds are not comparable. Okay. Now, Eric's mechanism is implemented by the Wharton School at my home institution, but not in the way that is described in Eric's paper. I'll answer your question in a moment, Devasis. Okay? So let me tell you what happens at Wharton. Bowdish's bound does not provide a course-by-course guarantee. So the mechanism is run, and then they see that some classes exceed the fire marshal's limit. What they do then is they go back in and they reduce the recorded capacity of the classroom and then rerun the mechanism. Now, when you do that, all of the incentive and fairness properties that Eric promises in his mechanism no longer apply, okay? Because of these adjustments to make sure that they get in under the fire marshal's limit. Okay? In our case, you can withdraw ex ante, we can guarantee just remove 4 seats from every classroom, compute the competitive equilibrium in the way that we are doing, and then you can throw back in the additional seats you removed, and you will come in under the fire marshal's limit. Okay? So that, I think, is the advantage of our approach over what Eric proposes. But there is something else that's going on, which is we are providing a competitive equilibrium result that is looking at basically the L1 norm as opposed to the Euclidean norm. Both of these results rely on extensions of what's known as the Shapley-Folkman-Starr lemma. And so let me tell you what that lemma is, and then say a little something about what the economic interpretation is of switching from the L1 to the L2 norm. Okay. So here is the lemma that we use, which has applications beyond competitive equilibrium. You give us a collection of binary polytopes, which have the property that the edge lengths all have, the L1 norm of the edge lengths are all less than delta. Pick something in the Minkowski sum of those polytopes, then we can guarantee the following. Notice, sorry, we're using the L infinity norm, okay, not the L1 norm. Okay? So this is our bound, the L infinity norm. Now let me look at the classic version of the Shapley-Folkman-Starr lemma. Notice it's a similar setup. The bound is on the L2, but it is in terms of the diameter of the polytopes rather than the edge lengths. Sorry. The bound here is in terms of the diameter rather than the edge lengths. Now, why should that matter? Well, I would like you to imagine 2 polytopes. One is the hypercube in m dimensions. Okay. Think of this as a choice correspondence where every object is identical in the eyes of the consumer, including the zero bundle. Okay. In m dimensions, what is the diameter of the polytope? It is root m. Okay. What is the edge length of any edge in this polytope? It's 1. Now, here is another polytope, which consists of just 2 points, the origin and the vector of all ones. Okay. What's the diameter? It's root m. What is the edge length measured using the L1 norm? It's n. Okay. Now, remember, the delta substitutes property is about the edge lengths as measured by the L1 norm. The hypercube you can think of as a setting where the goods are close to substitutes because the edge lengths are small, as measured by the L1 norm. Okay. The other case where you've just got the 0, 0 vector and the all ones vector, they're both in the choice correspondence. You can think of that as extreme complementarity. Now, extreme complementarity and perfect substitutes, we know competitive equilibria with indivisible goods always exist. Why? Because extreme complementarity just means take all the objects, put them together into a single bundle, and sell that single bundle using a single object auction. Okay. Perfect substitutes means the preferences for the goods are entirely independent of each other. Just run a bunch of single object auctions. In both those cases, competitive equilibria are easy to, existence of competitive equilibria is easy to establish. The difficulties arise when you move away from those two polar cases. Okay. Our result is about moving away from perfect substitutes. You can think of Budish's result as giving you a sharp bound when you move a little bit away from perfect complements. Okay. Did that make sense? Okay. And so let me answer Debasis's question, and then I should close for other questions. Debasis was asking, do you have some sense of what the implications of the deltas are? What does the delta substitutes property mean in terms of the utility functions directly? The answer is we do not know. We interpret the delta substitutes property as a condition. Yeah, it's given as a condition in the choice correspondence. And so copying Baldwin and Klemperer, and this notion is related to their notion of demand types. We think of this as some kind of version of Slutsky's, of a Slutsky condition. But there I'm simply engaging in the same propaganda that Baldwin and Klemperer are, and you will have to decide whether that's persuasive or not. So let me, so according to Vitali's rule, I should stop now to answer any other questions or if there's something somebody wishes to discuss.
We have still 10 minutes, so if there are no immediate questions, you can continue, and whoever wants to stay for questions, we can run some overtime. That's no problem.
Okay. Well, in that case, let me briefly tell you why there is a relationship between these kinds of results and the Shapley-Folkman star lemma. Here is the basic issue, and you want to think about this actually more generally than just competitive equilibrium. When I announce a price vector, I am basically announcing an option set of objects that you can choose from, or bundles that you can choose. And then from that option set, you are choosing a collection of bundles that maximizes your utility. This is your choice correspondence. So every agent is described by a choice correspondence. And so here is the choice correspondence of Mr. J at price vector P. Now, in a competitive equilibrium, what are we doing? We are looking for a bundle that is inside the choice correspondence such that demand is equal to supply. In other words, what we're doing is we're saying, wouldn't it be nice if S, the supply vector, lived in the Minkowski sum of the choice correspondences? If that were the case, supply meets demand, and then we could all go home declaring victory. Unfortunately, that is not the case. So what we're doing instead is we're saying we know the supply vector is in the convex hull of the Minkowski sum of the choice correspondences. We know that from the pseudo equilibrium, where I replaced your choice correspondence by its convex hull. Now your behavior mimics the textbook definition of consumer behavior. and then I can find a competitive equilibrium. But the bundle that I give you lives in the convex hull of your choice correspondence, which means I can interpret the bundle that I give you as a lottery over bundles. But I don't want to give you a lottery over bundles. I want to give you an actual bundle. And this is where things like the Shapley-Folkman-Starr lemma apply, which is you give me a vector y that lives in the Minkowski sum of a bunch of sets. What are these sets? These sets are the choice correspondences. Okay? Then I can find a bunch of vectors that live in the extreme points of your choice correspondence, whose sum approximates y. In this sense, approximates by the L infinity. Now, what we are using to get this result is the fact that these choice correspondences have their edge lengths are small. In the Shapley-Folkman-Starr lemma, the condition is not imposed on the edge lengths, but is imposed on the diameters of these polytopes instead. Okay? And I've tried to offer an interpretation or a context under which you might care about edge lengths as opposed to diameter, which depends on how you think about your preferences. Are your preferences a perturbation of substitutes, or are your preferences a perturbation of pure complements? Okay. Now, I said there's, this lemma here, I think, is of independent interest because I can think of any mechanism for allocating goods as giving you an option set. And then from that option set, you choose a choice correspondence. And then I want to make sure that the sum of the things in your choice correspondence add up to the supply vector. So as long as you can show that the choice correspondences that your mechanism generates have edge lengths that are small, then you could use this rounding result to get an approximate allocation. And let me end here then.
Okay, perfect. Thank you for ending on time. Do we have some immediate questions to that?
Yeah, Peter and then Helena. Oh, Peter, you're muted.
Thanks. Sorry about that. I have a question about sort of the practical implementation. And in particular, one of the beauties of competitive equilibrium is the reliance on prices to guide the allocation choice. And there's a great economy of expression that's possible as a result when people see prices and react to prices with demand vectors.
Right.
So I'm just wondering, in that world, sort of, can you sort of take that thought and run with it and sort of say that, well, yeah, so here's the practical advantage of your approach in recognizing that there's some issues of users, for example, describing their choice preferences over all possible
bundles,
price vectors.
Yeah, it's a good question. All of this machinery, the fundamental bottleneck with the use of this machinery, I think, is getting agents to communicate their preferences. So, for example, if you look at Budish's paper, agents' preferences are described by a von Neumann-Morgenstern utility function over all possible bundles. Perfectly fine for a theoretical exercise, but as a practical matter, it's not clear how you get 800 students each year at the Wharton School to sit down and give you their utility function for 2 to the 20 courses. Right? It's okay. So at Wharton, they restricted the preference language that the students were allowed to announce, in which they could communicate their preferences. So here is the specific restriction. You could assign a point to an individual course, and you could assign points to pairs of courses that could be positive or negative. So in other words, the only kinds of complementarity and substitutes that you could pick up with this language would be across pairs of goods. Okay? Now, it is an open question as to whether this language is rich enough to capture, all of their preferences. And I don't think anyone knows the answer to that question. Now, Martin Bichler has spent a lot of time thinking about this issue, about, how do you get people, what kind of user interface should you have for students to report their preferences? He has also a course allocation scheme set up at for the School of Computer Science at the Technical University of Munich. And their design relied on a lot of interviews with students to get an understanding of what were the things that were of primary importance to them in the design of the interface. So I think they allow something richer than just pairwise substitutes and pairwise complementarity, but I don't remember the full extent of the language. But Martin has a paper in which that's described. Okay, so I think this is really the fundamental bottleneck to the use of these methods, which is the user interface. The second question that I think you were asking was, one of the beauties of competitive equilibrium with gross substitutes is that there is a natural tetonement that converges to the competitive equilibrium. One might ask here, is there a natural tetonement that converges to this kind of social approximate equilibrium? And potentially, is there a version where you could have, as you say, the market maker participating in the tetonement, ensuring by either subsidies or burning supply that, eventually supply meets demand? And the answer is, I don't know, but I suspect not, for the same reason that there's an obstacle to tetonement once you go beyond gross substitutes, right? Which is, tetonement relies basically on the first derivative of the excess demand. And we know, going back to Stephen Smale and the 80s, that if you want any tetonement that converges always, it has to rely also on the second derivative of excess demand, which is just unnatural.
Yeah, and I certainly appreciate the impossibility results, but when it comes to market design, in some sense, impossibility results are irrelevant if in practice we can have the market perform incredibly well with high reliability and resilience, even though it violates a impossibility theorem.
Yeah. Okay. So then I think certainly a good question to ask would be, both in the Buddhist and this kind of setup where people are offering approximate equilibria, are there natural tetonements that would converge to these approximate equilibria? Helena, you had a question earlier.
Oh, sorry, that was a sign for applause.
I'm sorry.
Okay, perfect. So we are perfect on time, unless someone else has a question. Okay. If not, thank you again very much. It was a very enlightening talk. We will consider maybe thinking more about our course allocation in Mannheim. And let me just tell everyone that the seminar will meet again in 2 weeks, and our next speaker is Alessandro Pavan. So hope to see you all back in 2 weeks, and thanks again for the speaker.
Thank you all for your attention.